The common ion effect and buffers. So what's going on here? For example, the San Antonio, we have pretty good water. It comes from an aquifer, right? Except that means there's a lot of dissolved ions in there. So they call that hard, very hard water. And you can remove some of those ions. It's kind of odd. You can remove some of those ions by adding more ions, right? They add sodium carbonate. Well, the point is not the sodium. The point is the carbonate. Because if you add some carbonate, the solution is already saturated with carbonate, so it'll precipitate out mostly calcium carbonate. And that's what's gathering up on your faucets and all that kind of stuff. That's that calcium carbonate. But I think it must cause plumbing issues or plumbing problems in the city because there's nothing wrong with it. I mean, actually, the calcium's good for you. So, and thinking about calcium, if you drink some Coca-Cola, well, that's acidic. Your body has to buffer that somehow. It has to react to that acidity. And it does that mostly by leaching calcium from your bones. And, well, what can that lead to? Osteoporosis, I guess, in the worst case scenario. So the argument is that, ooh, beer's better for you than Coca-Cola, right? But, you know, beer has its own issues, okay? In your body, it's important that that pH is regulated in your blood. Otherwise, some serious things can happen. So buffers, they're all over the place, and they're important. I changed your directions a little bit here. I've got the below reaction may be used to describe the common ion effect, and I'm referring to the ionization reaction, or the Ka reaction, Daisy, of HCN. How would you write the Ka reaction, or the ionization reaction, or the dissociation reaction? They're all the same thing, of hydrogen cyanide. What goes on this reactant side? The CN. It's always the, not CN negative, Ka reaction. Anybody help her? It's HCN, right? The acid goes to, now you can finish it, can you? It goes to, right? Man, you got to know these backwards and forwards. This is the Ka reaction. Kb reaction, right? Have these in your sleep. Whoop. I guess you're right, HA. Right? So we're interested in this one. Bless you. Right? Okay. Common ion effect is really just, well, let's just see if we can see it here first. We want to know what's the effect on the total moles of H+. And what are they going to do? They're going to add some hydrogen cyanide. So Danielle, if you add some hydrogen cyanide, everything's at hunky-dory and equilibrium first. And then you add some hydrogen cyanide. So now you've got too much hydrogen cyanide. You're not at equilibrium anymore. So the equilibrium shifts. Would you end up having more or less H+? Danielle, if you add some HCN, you'd have more H+. Does everybody agree? Because now you've got too much of this. The reaction shifts this way, right? So you'd have more H+. Whose principle is this? Starts with an L. That's not an L. Le Chatelier or whatever, right? I think that's how you spell it. Is that Le Chatelier principle? Okay, sodium cyanide solid. Now the reason why that worked is because HCN is a common ion. Well, common compound, right? It's not technically an ion, but it's in the reaction, so it's common. So that's the common ion effect. Sodium cyanide solid, Alyssa. Do you see sodium cyanide solid in that reaction? No. I don't see sodium cyanide solid either, but I know the trick. You're not, when you see sodium cyanide solid, you're not supposed to look at what? Sodium. Ever. Pretty much ever in in chemistry. Why? What's that? It completely goes away. They call it what ion? Spectator ion is the common term for it. But the only purpose for the sodium is to do what? Yeah, it's positive. But to make this a solid. So you can put it in a bottle. You don't care about the sodium. What you're interested in is the cation or the anion? The anion. You're interested in the anion, right? Because the positive is cation. That's the only purpose of that lithium, sodium, potassium on pretty much any bottle, right? Is to get these anions in solution. So when I see this compound, I just see cyanide. Now it's a common ion effect. Now, Tegan, what's the effect of adding sodium cyanide to that solution? More or less H+? Why less? Does everybody agree? Because there's too much product, right? The equilibrium can't tell. It's just product. You have too much product. So it has to shift. That means less. Okay, that's the idea behind the common ion effect. It's also really the idea behind buffers. Crystal Munoz, can you read this first one for us and fill in the blank there?
A buffer is a solution that usually slight changes in pH when small amounts of
Perfect.
acid or bases are.
Excellent. Okay. Crystal Zamora, the next one. All.
Buffers?
Yes. Well, I can't hear. What? A little louder. All.
Buffers are mixtures of a conjugate acid and its corresponding conjugate base.
Perfect. Okay. Any solution, Jasmine?
Any solution of
Weak acid. Keep going. May.
acids can be used as a buffer.
Yes. Now, why weak? Why not a strong acid? You know what? If you have a strong acid in a solution, right? You want the whole idea of a buffer is that the pH isn't supposed to change. Okay. It'll change a little bit, but not a lot. So if you have a strong acid, you add a little bit of base, yeah, it's going to stay acidic, right? But add some more acid, it's just going to get, there's no base in there to react with it. So a buffer has to have both. That's really what this is getting into. Buffer solutions keep their acidity constant by reacting with acids or bases that are added to them. Because if you add an acid, something better react with that acid. You add a base, something better react with that base. So here's our buffer system. It's a weak acid, HF. Okay. So Allison, let's read this first one. Tell us what you think.
In the system, the conjugate acid present is H.
Mm-hmm. Perfect. Okay. Keep going, Diana.
If any acid is added to this buffer,
We're adding an acid. So what can react with an acid? Only a base. So which one is the base? Is it the HF or is it the F? We just said it was the conjugate base is the F, right? So F has to react. So keep going, Diana.
reacts with the added acid which produces HF.
Which produces HF. The conjugate base reacts and it produces HF. And keep going.
This keeps the pH relatively constant.
Okay.
However,
Okay, let's finish it. Go ahead.
However, if any base is added, HF
Good.
will react and produce F.
Yes.
It also keeps the pH relatively constant.
Okay. So relative. I mean, it's not going to be perfect, but it's going to keep the pH relatively the same. Okay, so now we're going to get a little more specific here, Erica. If
If 250 ml of
Oh, how do we say that? Molarity or molar? Molar. Molars are really the common one, I guess. But we're adding an acid. We're adding an acid. So something has to react with it, and it's going to be the conjugate base, which is F. So is the amount of F going to go down, increase, or remain the same? F has to react. Right? If F reacts, doesn't it kind of, right? If, I don't know, there's 10 Tegans in the room, and every time a Tegan eats a chocolate chip cookie, she turns into this glutton, right? Not a Tegan anymore. So the Tegan reacts with a cookie. So Tegan eats cookies, Tegan disappears, right? That makes sense? So if F minus reacts, F minus has to decrease, has to disappear on you. By, here's the question, by how much, Monica? By how many moles of F? Okay, good. Now she's looking up here. It's not the right answer though, right? They want moles, not molar, right? So if you're giving, to doing this buffer stuff, it's really nice to be able to see how to calculate moles quick. What was big M? Big M was what over what? Moles over liters. So you can set up the big M equation to figure this out, but I suggest no. Just realize if I multiply big M times liters, I have moles. And that's why they give you volume and concentration so often, because liters times big M is moles. So you pretty much just move the decimal place how many to get liters? 3 times. So I'd end up with 0.25 liters, and then times the 0.1 moles per liter, you get 0.025. So the moles of F minus will decrease by 0.025 moles, because that's how much acid you added. And it reacts 1 to 1, right? So for every 1 mole of HCl you add, 1 mole of F minus is going to react. It's 1 to 1. Okay. So Gabby, that makes sense? Okay, so Sabina, just finish this then. And what is F minus getting converted into? We said it was getting converted into HF. So the number of moles of HF will F minus grabs onto that H and makes HF, right? So the F minus is disappearing. The HF is appearing or increasing. So HF, the moles of HF has to increase by how much? Anybody? 0.025. Exactly. It's all one. Everything's 1 to 1. Okay. So to get moles, just multiply what 2 things together? Liters and molarity, and you'll have moles every time. So if you ever see a question and it has the word buffer in it, man, just instantly jump right down here. Because you can get the pH of the buffer right here. Here's the pH of the buffer. The Henderson-Hasselbalch equation. So we're changing it a little bit. I got rid of the concentration, and I'm just writing, what's my equation? I don't have concentration anymore. I just have what over what? Moles. How can I do that? I'm trying to save you some work. concentration is what over what? Moles over liters, right? So the liters isn't a buffer just, I mean, that's it. There's one volume, right? So I'm dividing by the total volume, whether it's top and bottom. It really doesn't matter, right? So you really don't need to calculate concentration. You can, but then you have to divide by the total volume on top, divide by the total volume on the bottom. It's the same volume. So they just cancel. This equation is so much easier to mess with, I think. It's the exact same equation, though. Okay, now a lot of you have had lab. Lab this week is 28. And so getting the moles, no big deal. We already talked about it. Multiply volume times molarity. Just make sure volume's in liters. How do you get this? If you've had lab, you know. P is the negative log of Ka. Where do you get these Kas? You got to memorize them, Vivian? No? You get them where? Tables. Yeah. Okay. So pKa is negative log Ka. Okay. Good. How do you plug that in the calculator? Exactly. Let's figure that out. Okay. So we can go to the boards, figure this stuff out. Yes, Allison. It's good for you. Get some energy. Get some exercise. Right? If you need some chalk, I have some. You want some new chalk? There's some up here.
Thank you.
Okay. A buffer is prepared by adding 50 mils of 0.25 molar sodium cyanide to 40 mils of 0.2 molar hydrogen cyanide. What is the pH of the final buffer solution? Okay. So it's a buffer problem, so I gave you the buffer equation. You can work up here or right in here. You have your own board. Okay. Okay. So identify, pretty much just you got to figure out the moles, right? And then we'll have to do what Crystal was asking about. You got to figure out how to get all this in the calculator, but see if you can get the equation written out first.
Big M equals
Moles over liters. Yeah, you're solving for moles. Or just remember, multiply big M times liters, you have moles. That's the easy way to remember it, I think. It always works. Multiply big M times liters, and you'll always get the moles. And remember, the conjugate base has to be up on top.
No, we get the K for the acid.
And they gave it to you. Okay, Daisy, I think they have point, either your top part is, right? I think people are getting point, what are they getting? 0.125. Where's 0.0125? You take, all right, 0.05 times 0.25, you should be getting 0.0125, right? So this is the one we messed up on.
Wait,
All right.
25 cents.
That's 0.0125. This one works, but the bottom one should be 0.04 times 0.2. Okay.
So after I divided these two, I would press log, right?
Yes.
I did, and I got this.
Okay.
I don't know what to do.
Well,
Is
you have
it
4.9, 10 to the 10.
It is the
Log.
10 to the negative.
So don't you have 9.3 here?
How did
What is that? 0.008.
you get 9
Just put it in your calculator. Hit log.
Got it?
So what'd you get as the final answer? 9.5. So make sure you can get 9.5 before you move on, right?
The next one only has an acid.
Okay. Make sure you get this 9.5. Get it all in the calculator and make sure it all makes sense. Okay. Once you get it all to make sense and you got the 9.5, go on to part B. Okay. We're going to add some acid.
This is only the moles for us. Yes.
Right? So remember that if you're adding acid, that means what reacts with the acid? The conjugate base does. So you're going to be writing pretty much the exact same equation and just modify it. Right? Just modify it. See if you can figure this out.
I think you add it to the moles of the acid together. Moles of
Right? The moles of a conjugate base has to decrease. The moles of conjugate acid has to increase.
So now we're going to use the KB. No. We still use KA?
All right. So I'm getting you started on part B if you don't have it yet. Right? Won't it be, because nothing really changes in that equation, right? pH equals pKa, and I just copied my answer from the top one, plus the log of the moles of the conjugate base over the moles of the conjugate acid. So what do I do here? Do I add or subtract on the top? The conjugate base. What's going to, see how I just copied these numbers? I took my work from part A. That's where all the stuff is coming from. See where the 0.0125 is coming from and stuff? The 0.08? Okay. So do I decrease the moles of conjugate base or do I increase the moles of conjugate base? What happens? I'm adding HCl. It has to decrease, right? Because the conjugate base is the only thing that can react. So that better be a minus sign. Let's change that to a minus. Okay. The conjugate acid, it has to decrease or increase? Increase, because it's getting converted into it. So I have a plus sign down there. Now you got to figure out what the number is going to be. Exactly. You get the moles of the HCl. Just multiply them. But make sure the volume's in liters. Mm-hmm. So it had to be right up here, 0.04 times 0.2.
Don't they just cancel out then?
Doesn't what cancel out?
Those last two values.
No, it's plus and minus. It would. You're right if it was times. But it's plus and minus, so it won't. So did you get around 9.4? Okay. So hopefully you're getting somewhere around 9.4. Now, what you can do is you can help yourself out by this. It should make sense. If you add an acid, the pH should go up or down. If you add an acid to something. If you add an acid, the pH should go down. So did the pH go down on you? Yeah, it did. This didn't go down a lot. That means the buffer's working. Okay. So if you get 9.4, go on to the next one. If not, let me help you out. Make sure you understand where all this stuff is coming from, because this is what your homework is all about. Make sure you're getting all this in the calculator right. And the next problem has a real twist to it. You want to make sure you understand the next problem. You want to get this one done first. I got about 9.4. Good. Yeah. Does it work, Danielle?
Which one are you talking about has a twist?
Oh, this is part B.
Okay. So how do you differentiate between the conjugate?
Conjugate acid.
Yeah.
What I do is, a big hint is there's no H. And you don't look at the Na.
So if it's...
This has to be the conjugate base.
Right, because the one with the H is the acid.
Yeah. Or the one with the more H's is the acid.
Okay, got it.
The acid's also in the table. The acid's also the one that goes with the Ka.
Okay.
So there's a lot of hints that you can look at. Try the next one. Part B is where there's a twist in the next one. See if you can figure it out. Negative? Is it negative there? I think I screwed up. That should be a negative sign, isn't it? If you take the log of it, don't you get a negative number?
Yes.
Yeah, so it has to be. Yeah, you have to. Yeah. Right. Yeah, negative 0.12. About 7.34 or something. Depends on how many digits you're carrying. So did you get about 7.3, hopefully? Did you? Okay, we got 7.34. Okay, now, okay, this is where the problem comes from. What would, oh, let's make sure everyone's on this part yet. Did you guys finish part A and get 7.34? Almost? Okay. Make sure everyone's there first. Okay. So in part B, it's very similar to what we did earlier, except are they adding it to the whole buffer? Or are they only taking part of the buffer? What are they doing? They're taking part of the buffer. So if you go back to see how we did the previous problem, right? Here. Right here was the moles of conjugate base, the moles of the conjugate acid. But we used those numbers because we used the whole thing. If you would have only used half the buffer, you would have put a half in front of this one and a half in front of that one. If you would have used a third of the buffer, you would have put a third and a third. 100th, you put 100th and 100th, right? So pretty much you're going to do the exact same thing here. Just figure out what the fraction is that you put in front of these. Okay? So do the exact same thing, just figure out what the fraction is. Whoop. See if you can get that. You got about 6 minutes.
So we just put it, the fraction in front of that?
We don't have it. You have to multiply that out. And then you're also going to have a plus or minus thing here, right? Because you added some acid. Right. So I guess it would look like this. Right, so we got to figure out what those question marks are, right? So our moles of conjugate base, we have to multiply it by some fraction. And then we have to either add or subtract something, because we added something. We added some acid. Same with the moles of the conjugate acid. We have to multiply it by some fraction and add or subtract something. The second part, how do you do the plus or the minus part? Good. It'll be a minus and a plus. And what number? Erase. 8.75 times 10 to the negative 3. Or I could just write 0.025 times 0.35, right? Does everybody agree with that? Right? Everybody agree so far? Did I lose anybody so far? So, Danny? So I mean, before we fill in the question mark part, the fraction, does the rest of it make sense? Okay, let's figure out what that fraction is. Has to be something over, that's what fractions are, right? There's something over something. What will the fraction be? I hear 1 over 4. Why? Well, we're interested in, this is the moles of the conjugate base. And what is the volume? The volume they took is 100 mils. But what was the total volume? It was, what's the total volume of the buffer? Because they said of the buffer. So the total volume of the buffer is 0.55 liters or 550 milliliters. Is that right? So that's the total volume of the buffer. But we only took how much? 100. So the fraction would be 100 over 550. All right, so it's kind of an ugly fraction, but that's what it would be. Same fraction down here. It'd probably look better if we figured out what that fraction was and wrote that in. So and the reason why we have that fraction is there because they didn't use the whole darn buffer. And they're going to have some homework questions like that, where they don't use the whole darn buffer. So see if you can get an answer out of this. Whoop, minus. So did you get around 7.13 or so? Great. Perfect. That's what I got too. Around 7.13.